morning, good afternoon, good evening, wherever you are in the world. This is absolutely wonderful. We're so happy to bring this to you on behalf of Kwekwa. Eamon Darcy is my name. I'm the founder and operator of Kwekwa, the Quantum Education Center of WA. And we have an absolutely packed day today. And this is all on behalf of Q Girls, which is an initiative to get young schoolgirls involved in quantum computing. At the moment, we really want to address the underrepresentation of schoolgirls in quantum computing, in STEM subjects in general, but in our case, quantum computing. There is no need for it. There's no need for it at all. And we've got things that we can talk about to help. But Q Girls, under the leadership of Donna Buckley, who you'll be meeting soon, is designed to address this. It's not going to carry on. We're not going to allow it to. And here we can see the agenda. Sorry, the previous slide was Jeff Bezos basically saying, Jeff Bezos said this 6 months ago, that quantum computing is the technology of the future. It will literally change everything. And he's so right. Here's our agenda today. I'm going to very quickly mention the mission, and then we're going to go to a pre-recorded interview with Sadia Sakib, one of the presenters today, myself, and Anisha Musty. Anisha is an amazing young lady. At the age of 14, she started Community, which is a very well-known, well-respected quantum startup, and out of New York. And she did it when she was 14. It's amazing. It now has thousands of members. She's only 17 now, I might add. She has thousands of members worldwide in many, 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 many countries, and lots of things happening. I've actually written one of the courses there. You can go onto the Community website and actually attend one of the courses. Most of it's free, and it's so exciting. And I can't believe she's done it. She's interesting to talk to. Donna and I are absolutely dedicated to getting one of our Q Girls to do something similar. We're going to have pathways for you towards further education and towards jobs in this industry, because CSIRO has said the jobs are going to go through the roof. So let's just go through the agenda. I've basically done the first one. And then we'll go on to the recorded interview very shortly. Then I'll introduce the wonderful presenters and panelists we have. And as you know, we all had a get-together last week, which was fantastic. And I love the questions. This is all about questions. What we want to do today is get young people, young schoolgirls, interested in quantum computing and quantum physics. So ask questions. All we want to do is ask questions. You can ask questions if you're watching as well, but our panelists will be asking questions too. And then we have the wonderful Sadia Sakib. She's only 16, and she's going to talk about quantum entanglement, which is not only the most mysterious thing in quantum physics, it's the most mysterious thing in the whole world. I love it when people say to me, oh, don't we live in a beautiful, wonderful world, a wonderful universe? And I always say, if you don't know quantum physics, you don't know how wonderful this world is. It is weird. And Sadia will be helping us. And then we'll have, and this can go on for as long as we want. We have questions and answers. Sadia, Anna, and myself, and maybe some of the panelists will answer some of your questions. But without any further ado, let us go into yesterday's interview with the wonderful Anisha Musty. Hello, Anisha. Are you there?
Hi, can you hear me?
Yeah, I can hear that New York accent loud and clear. How are you?
I'm so good. I'm so sorry. My phone, I have to be on my phone right now because my computer isn't letting me join this link for some reason. I'm gonna try to join on my computer so you can get like a full real recording so it looks good. But yeah, how have you been?
Yeah, oh, look, terrific. And I'm here with, can you see the screen?
I can.
Oh, great, because I'm here with Sadia Sakir, who's doing one of the talks tomorrow, one of the presentations tomorrow for the Q girls, the quantum pseudo-telepathy, the science. What an interesting subject that is. But yes, Sadia thinks you're wonderful, so I'll let Sadia say hello to you.
Hello, how are you?
Sorry, could you say that one more time?
I said hi. I said hi. How are you?
Oh, I'm good. How are you?
I'm good. I'm good. I have a few questions for you. I know Eamon does as well.
Oh, that's
Do you
awesome.
wanna
Yeah,
get
go
started
for
with
it.
that?
Yeah, you start, Sadia.
I wanted to ask how and when you got interested in quantum computing.
It's been a long time now. I think I was 14 when I started.
Mhm.
It was pretty much just I found out about it through some like hype videos, I want to say. And then the from there I was just like, oh, let me look into this because I thought it was very interesting, like as technology. And I've always been into things that maybe have like a lot of room to grow, something that maybe isn't as developed. It has a lot of like new stuff to discover inside of it. And that's kind of what appealed quantum to me. And yeah, I mean, I pretty much just for some reason felt an instant connection to it and started looking into it. And yeah, that's pretty much it. I started like self-teaching myself it. I live in New York, so I can go to a lot of events, and this was pre-COVID, so there were a lot of in-person events happening for quantum, especially IBM has their headquarters here. So yeah, I had a lot of opportunities to like meet people, and the community is just awesome, as you probably know.
Yeah, that's wonderful. What would you say you like the most about quantum computing and physics?
I mean, I think physics is one of those things where it's so unique in that everything you learn is like it's almost foundational to every other field. Like you fit everything in physics, it's like it is like you're learning about nature and like how the world works at like its most fundamental level. And I think that's probably like what excites me the most. It's like the idea that like you're working on something that like forms the core of like every other scientific discipline. But also, I think physics is so interesting because it's something that like in order to advance in physics, you kind of almost have to accept absurdity. Which is
Mm.
like, for example, like when people were like thinking about like atomic structure, like you have to question like the basicest of things. Like it used to be that people thought like atoms were like indivisible blocks, right? And for it to be anything else would be absurd. But you have to question that. And that's how you make progress, because that's not true. Someone had to question that absurd. Same thing with like the heliocentric model. Like it would be absurd for it to be anything except the heliocentric model, but someone had to question it anyway, and that's how they make progress. And it excites me because it means like in my everyday, like there's so probably a couple many things that we accept as true that are just not right now, and we probably have to like question that. And it excites me because it means that I have to think from about everything like from my own perspective, question everything, like do my due diligence. And I think there's just so much more room for me to like have that creative freedom.
Anisha, thanks for telling us about when you first got involved with it at 14, which is amazing. And it's amazing that you didn't just, it's not like you just read up on it. You actually started creating things. And of course, I think at 15 or 16, you created community. So I'm interested, where is community at the moment? How many members do you have? What countries are you in? And tell us the community story, because there's going to be a lot of young high school girls watching this and they think it's impossible, but you've done it. So yes, please tell us.
Yeah, I mean, community was pretty much started maybe also when I was 14, like a couple of months after I started, because from when I was saying, as I went to these events, I was meeting all these awesome people. But what I noticed was that there were literally no young people, no college students, no high school students, pretty much just like professionals, like
people who had their PhDs, people who had graduate degrees, maybe people who didn't even have those degrees and like were also working in quantum regardless. It was just, there's no young people. So I had an idea, I wanted to start a hackathon. And this hackathon was just supposed to get some like general interest in quantum, like maybe even for my school. It's supposed to be in the NYC area. So yeah, I had that. But as you know, the beginning of 2020 was COVID. So my hackathon unfortunately got canceled like a week before it was supposed to happen.
Oh.
Very, very unfortunate. But I mean, it was actually like such a blessing in disguise, because what ended up happening is we had this, but prior to the hackathon, we were getting so many emails from people in like different states. We were having people like, I don't know, you guys, I think you're both from Australia, so you might not know the US states, but people like in Idaho, which is like the other side of the United States, like were emailing us being like, will you come to Idaho? Like, will you do a hackathon in Idaho? And we were like, I don't know if we'll do a hackathon in Idaho, but maybe. But yeah, after COVID happened, we're like, why don't we just do something online for all these people? Because there was like a rise in virtual meetings, all of these things. People were getting more comfortable with them because they were just needing to become a way of life. So our online events actually had people come. We were able to meet people in Idaho, meet the people in New York, also like people like you guys from Australia, people from India, people from like the UK, people from everywhere. And I think that's pretty much, we were just like, this is working. People like want to do this. People want something for young people in quantum, and that's pretty much like, let's actually make this community. Let's make this something bigger. Today we have around 25,000 members. This is people who've taken our courses, been in our events, people who read our newsletter, and yeah. We have so many different countries. Like some of the most exciting ones to me are, we have Syria, we have Sweden, we have Zimbabwe, we have pretty much every US state, Canada, we have Tunisia. Yeah, some awesome countries in there that it's so exciting to meet people from there too.
That is just amazing. Congratulations is the only word that jumps into mind. I mean, to have that many members, what is your advice to someone like Sadia, 16 years old, I don't want to embarrass her, but she's a very intelligent lady, and she's right into physics. She's actually studying, in fact, you say, Sadia, what are you doing with time and your thesis?
I'm writing up about the concept of time and light and how they kind of change and bend around things like masses and gravity why does that happen, kind of. So yeah. I've got another question as well. If you want to go first.
No, you go, Sadia.
Okay. How does it feel being such like an inspiring figure for women and girls in STEM alike, especially for POC women?
Oh, I mean, that's nice to hear. I mean, I feel like it's hard sometimes to like really tell, but I think at the end of the day, what I want to be is like representation. Because I know when I like look at like role models in the field of like who I want to be, like I looked at the quantum field, and I don't really know of any like super prominent women of color in positions of like authority. And then if I do want to idolize someone, I have to like idolize a man, usually a white man. And then like it's very difficult for me to do that, because like I just don't have like any way that I achieve success will not be the same as the way they achieve success. Like I grew up on my high school's debate team, and it was kind of the same idea as like when I wanted to become a really good debater, like the only people who have really done that are white men. And like for white men to do it is a very different story, because like the way they speak is immediately perceived as differently than the way I talk. So I think at the end of the day, it's like when you achieve like a stage or like a platform or people listening to you, the most important thing to do is just like be someone just, I almost should be like, I've done it, other people can do it too, because like that's all it really is I I think it's just me achieving this platform is like important to me to be like representation.
Oh wow, that's a fantastic answer, and I can understand it completely. It fits in to what we're doing here with Q Girls.
You see girls and like guys joining at an equal rate in the beginning of a career. So like if you go to an 8th grade like coding class, you'll see 50-50 guys and girls about. But when you go to an 11th, 12th grade coding class, you'll see that around 40% of those girls, 80% of those girls have quit, and now you have 3 girls and like 12 guys in the class. So it begs the question of why girls don't stick with these fields. For me, I've always found that like STEM fields become almost kind of a boys club, as like it's just a self-fulfilling prophecy of guys stay in the club because they have other friends in the club, versus a girl who joins is immediately greeted with like an abundance of men and like not as many women, feeling like an exclusivity factor, and then they just don't want to stay. So I think some people obviously like don't mind that as much, they stick with the activity, but it does weed out like so many good candidates in STEM. And it's just something that like people have to brute force through until it's fixed, because otherwise somebody's just got to stick with it. Yeah, so I think my number one advice to be like for women to like fix that is to don't give up on it yourself. If like the situation is bad, remember that like what you're doing is worth it, and you're doing it for yourself, and like you can create what you're missing. And I think that's a big thing, is like if you're missing a community, make one. And like, yes, that means your life is harder because it would be awesome if like somebody else did it, but sometimes you just got to do that because you are just like the first person or like one of the first people to like experience that. But then yeah, I think community is huge, because like what you guys are doing at Q Girls, you're bringing a bunch of women together about quantum, so they already know that like they're not the only woman in this field, and they have like people to rely on, people who actually have like the same career struggles as them that they can speak to, about people who can like serve as representation for them, as I was talking about, all of those things. But yeah, it seems like you guys are doing a really good job of it, so stick with it.
Anisha, it's been absolutely lovely talking to you. Thank you for finding the time. It's been really special, and we're going to include this interview in the presentation tomorrow. And
Awesome.
So it's a big thank you from everybody, and hopefully we'll talk to you soon. And let's get this quantum computing world happening. Wow, how did she do that? You know, to create community from the age of 14 to 17, 25,000 members. Oh, I wish you worked for me, or I worked for her. I really do, which I have done, as it happens. Fantastic. So, all right, next on the agenda, let me bring up the panelists, these wonderful people, starting with wonderful Ellie.
Hi.
Jane, hi everybody. Raja
Hi.
and Donna. Right, are we all here? Yes, we are. Donna, why don't you kick off the show? You just a few minutes. Tell us about yourself and what you hope to get out of being part of Q Girls. Oh, you're on mute. Donna, you're muted at the moment. Okay, just can we go to Ellie? Can you?
Yeah.
Is that you, Ellie?
Yep.
Okay. We'll have a look. It's at your end, Donna. So we'll go over to Ellie. So Ellie, if you'd like to tell us about your great news that's happened and what you want to get out of this. Yeah.
So I was just accepted into the National Youth Science Forum for next month in January, which is really exciting. And so I hope that this and that next month as well will give me, I don't know, opportunities to see different STEM careers and see different applications of science and everything, which should be really, really interesting, I hope.
Yes, fantastic. Thank you, Ellie. And that's a really great congratulations. You can only go up from there. Wonderful. We'll go around the table. So we'll go Jane.
Hi. Okay, I'm Jane. I was at John Curtin as well, and I just graduated a few weeks ago. I was in the cybersecurity course with Miss Buckley, and at the moment I'm working on a video game.
Wow. Yeah, cybersecurity, I don't know whether you know, Jane, is a huge area that's going to change in the quantum world.
Yeah, with the factorization of the RSA systems, right?
Oh, brilliant! Exactly. Shaw's algorithm. Yeah, so it's basically what Jane is saying. Pretty soon, well, I shouldn't say that because it could be a little way off, but you know, decryption that up to now takes 1,000 million years can be done literally in a few minutes. And that is a whole big area which we can't sort of go into now. But thanks for that, Jane. I'll pass over to Raja. If you can tell us a bit about yourself and what you want out of this.
Yeah. Can you hear me?
Yes, we can hear you fine.
Okay, that's good. I'm Raja. I've been really interested in cybersecurity and computations in the past few years. I'm quantum physics, but the opposite to me, and it's really interesting. So I wanted to learn more about it.
That's fantastic, Roger. You're exactly the sort of person we want to be talking to. And Donna's very well aware of the huge change that quantum computing, it's called PQC, post-quantum cryptography. And the US government has just migrated all of its documents. And imagine how many billions of documents that is and how long it's going to take and how much it's going to take. They're moving it to a post-quantum cryptography server. They're taking it off RSA, putting it onto a PQC server. And the reason for that is that these hackers are actually hacking, they're doing what's called SNDL. They're hacking transactions, they're storing them, knowing that they can decrypt them in a few years' time. It's a crazy, crazy world at the moment. Over to you, Hope.
Hi, I'm Hope. So I haven't really had much experience in like anything computers or quantum. So, but I always have had like an interest in it. And so I feel like this could be a great like introduction and maybe like a bit of a starter course for me because I find it really interesting.
Oh, that's fantastic, Hope. Yes, it really is. Everything to do with quantum computing is interesting. You'll see that during the presentation. And now, Donna, can we try your microphone again?
Hello, can you hear me now?
We can hear you fine.
Fantastic. I'm just so inspired and just listening to Hope then saying I'm just starting out and I don't really know much. I'm just curious. And then I look at what Anisha was saying earlier in her presentation that, to build a community as a 14-year-old, and I do know, I think, Hope, you're just 14 as well, and you're our youngest panelist today, that we can, this is all ahead of us. We all have to start somewhere to learn about these things. And I'm really inspired with you, Eamon, to set this up, to have an inclusive environment. There is that thing of it just being, older white men who are in this STEM space and computing, and through networks like Witwa. Sorry, no offense to you, Eamon, but like through organisation, like for you just supporting, but us women need male supporters as well, and the organisations in Witwa. And I do know there's a few of our male students in the background who are really happy to help support this. But we've learned over the years, we do the Girls Programming Network, and that's been Australian-wide and with so many members, that girls are more comfortable learning with other girls. It's providing that support, and we want to see a change where that girl isn't the only one at university studying quantum science, mathematical sciences and technologies, but she's got a community around her, like other inspiring Australian communities, the Australian Security Network, Women in Security, WITWA, and Girls Programming Network. So they've really inspired me, and I hope that we can build something here to help get into the quantum space and support our transition to a quantum era. So I'm pretty excited by this.
Oh, that's wonderful, Donna. I am too. And let me completely assure you, my thumbs down is that it is wrong. Our situation at the moment where girls feel uncomfortable learning the most important technology in the world is absolutely unacceptable. And you know, Anisha said everything, didn't she, about the inclusivity. We have to include everybody, and it's got to stop. And it is stopping to some extent. Okay.
And one of the things I've really noticed, and as being a teacher, sorry, I'm going to but being a teacher for 20 odd years, what I notice is that girls are very good at mathematics and science, but sometimes they don't have the confidence of their own abilities, and that giving that space, and to that, because maybe us girls are a little bit perfectionist girls. I don't know if you agree sometimes that, you know, you think you have to know all the answers first, but it's okay not to know. We can learn and discover, and I'm still learning. I'm here, and I bet you, Jane, I know for sure that Sadia and that know a lot more than me, but I'm still learning, and we're just lifelong learners. So sorry.
Oh, they're very wise words, Donna, as per usual. And let me tell you something. If you want to know everything, this is the wrong industry for you, because nobody understands quantum computing. But look, let me move on. Lovely to see you all. I'm going to put you backstage. Get your questions ready. And I'm going to bring on the presenters. And basically, it's just going to be Sadia presenting with Anna and I backing up her comments. Here's Anna and Sadia. Oh my God, I've got so many things to click. Hi, everybody. Anna, maybe you could quickly introduce yourself, and then we'll go to Donna's presentation, and you and I will comment on that, and then we will start the question and answers.
Okay, my name is Anna. My pronouns are she, her, and hers. It wasn't always like that. In my youth, I studied physics as a man, and it was difficult to really commit. And about 5 years ago, I decided to transition to female, and I also resumed my study of physics. And I love it. It's a great life. And quantum computing is really what I'm all about. I just founded a corporation, the Quantum Physics Corporation, and there are actually people on the team working. And that's what I have to say for now. Thank you.
That's wonderful. Thank you. Okay, what you and I will be answering a lot of questions later. So I'll put you backstage, and let me quickly get on to Sadia. So get the ticking stumping. Right, Sadia, we'll go straight into your presentation if that's okay with you.
Yeah. Hi, everyone. Today I will be giving a simplified explanation of quantum entanglement. If we could go to the next slide. So what if I told you that there was a form of communication that was effectively faster than the speed of light? There is. and that is the subject of the presentation today, which is quantum entanglement. Next slide. So before I explain quantum entanglement, I need to explain quantum superposition so everyone knows the full extent of what we are talking about today. So quantum superposition is essentially when a particle exists in multiple states at once. And you might be going, what the hell do you mean by that? But it's kind of like, the analogy I like to use when explaining quantum superposition is if you imagine a coin, it's got heads and tails, and if you spin it, it can either land on heads or tails. Similarly, particles like electrons, I will be using the spin of up and down. When they spin, when they rotate, they are existing in the state of spin up and spin down at the same time until we measure them. So that's essentially like when the coin stops. That's when we know whether it is spin up or spin down, or heads or tails. And on the bottom left is a photo of the possible spin outcomes. And that's kind of like saying each electron is directed by its own kind of characteristics, and it's we call it a wave function in physics, but you can sort of say that it's like its description. Next slide. This is a quote by Niels Bohr that I like to use. It's called "Nothing exists until it's measured," and that ties in with quantum superposition. That nothing really is real until we look at it or we observe it. Next slide. So what is quantum entanglement? So it's kind of like this strange, unexplainable link kind of between two or more particles at a distance that can be light years apart. So if you say there is a electron on Earth and it's entangled with an electron on the moon or Jupiter or wherever, when one changes its spin, like I explained spin before, when one changes its spin, the other instantaneously changes spin. And that's why we say that that information between those two electrons that are entangled, or two particles that are entangled, travels or transfers faster than the speed of light, which is crazy to think about, because in physics, there's this established idea where nothing can be faster than the speed of light, but it's been proven that information can transfer between particles faster than that. Next slide. So quantum entanglement to Einstein and loads of other kind of theoretical physicists was really confusing, and Einstein even called it spooky action at a distance because it went against his ideas that he created himself about physics and stuff. Next slide. So this year there was a Nobel Prize for Physics, and there were three renowned physicists that won: Elaine Aspect, John Clauser, and Anton Zeilinger, and they were all researching quantum entanglement. Now, in their experiment, there was two observers, Alice and Bob, and they both had electron detectors in their hands, and they would randomly rotate like the spin orientation of those detectors. And two entangled particles were sent out in Bob and Alice's directions. They were standing at a distance. Next slide. The entangled particles were both spinning up and down until they were measured, like I explained superposition before, and they obviously had random orientations on the device. So when those particles reached the detectors, one of them would go off, but the other wouldn't go off because they wouldn't be in opposite orientations. as I explained prior to this, you can have it spinning up and you can have it spinning down, but when you want both of the detectors to beep, you would have to have it so that both particles were spinning in opposite directions. So it's only possible for the electron, when it hits the detector, to be spinning up and then communicate that information to the other electron so it spins down when both of them are measured. And that's when both of the detectors beeped. So yeah, that's how we know that quantum entanglement is actually real. It was proven this year. Next slide. Wormholes and weird things. Actually, this was a experiment that I was looking into last week, I think. It was only done last week by MIT, Caltech, and I think Harvard researchers. Basically, the idea of wormholes is that they are kind of like a rip in space-time. I think there's a next slide that will show you a picture of one. But wormholes will have information passing quicker through them rather than going around them, which would obviously take more time. So what they did was they got two quantum computers. We call the processors in them qubits. And they're basically like quantum particles in superposition. So those particles kind of formed a 2D wormhole because there was instantaneous information passing through them rather than having to go around the wormhole and travel slower than the speed of light. So the physicists kind of essentially created a holographic wormhole through quantum computers, which is crazy to think about. But yeah, that is what happened. It's not an actual wormhole, because if it was, then we wouldn't be here right now. But yeah, that is what happened. Next slide. Yeah, this is what I was talking about. So they both have this thing called duality, where the wormhole has an easier path for particles to go through than normal space. And as you can see, entanglement is sort of similar because of the way those two particles are linked. It allows them to have information traveling through them faster than light, which is similar to a wormhole. Yeah, I think that is all. Thank you for watching. Does anyone have any questions or comments?
Wonderful, wonderful. Well done indeed. I'll just bring Anna back. Okay, Anna, would you like to say a couple of things, and then we'll get questions from the audience. You can, if you're watching this on YouTube or Facebook, you can ask questions and I'll find them here. We have had a good look from a Facebook user, so that's great. Anna, would you like to comment on, first of all, congratulations, Sadia. Thank you for explaining that such a complex issue so easily. Anna, would you like to say a few things?
Oh, sure. Thank you for your explanation, Sadia. I want to say, speaking as a physicist, that your presentation was right on. I mean, you really got it nailed. And as far as information is concerned, there's two kinds of information. There's quantum information, and there's something else, the information that comes out of measurements. And the quantum information can travel faster than light. But, well, for instance, in teleportation, Alice's measurement is communicated instantaneously to Bob on another galaxy. But Alice can't actually use that. For example, supposing she wants to tell Bob what her marital status is, she can't actually do that faster than light. So there are some deep mysteries around information, and frankly, nobody understands entanglement, and I'm going to say nobody understands information really, and what it actually is and isn't. So that's what I have to say about that.
Yeah, that's wonderful. And I'd like to endorse your appreciation of Sadia's technical explanation and presentation. For 16, Sadia, you're, certainly walking in the steps of Anisha at the moment. I want to add one thing, just to say that your takeaway, anybody watching this, your takeaway is that quantum particles, which is basically anything smaller than an atom, which you are made of. So we are all made of quantum particles, and they act very, very weirdly. We cannot understand what they do. Like Sadia just said, we've got this entanglement that we don't understand. Reality is not what we think of it at an atomic level. The real reality is happening, and it's weird. And it means that we can do weird computations. Not only can we do them exceptionally quickly, we can actually do things that are illogical. And Anna's actually performing that at the moment. But what we'll do now is we'll move on to questions. There's no questions except the nice comments saying how wonderful it all is from the audience. So what I'll do is bring on the panelists, and let's get some questions from the panelists. Well, calm down.
Oh, I had one question about
Okay,
it.
just hold on 2 seconds. We're all coming back. So, great. Who had a question, sorry?
Oh, so that was me, Ellie.
Ellie, wonderful. Please go ahead.
I was just wondering, is there a limit to the distances that particles can be entangled? Or have we measured that far yet, or anything like that?
Oh, should I answer that, or do you want to answer it, Anna? Or Sadia? In fact, Sadia, you answer it.
I don't think
she's backstage. You might have to answer it later.
Oh, she is. She's off stage. Thank you.
Hello. I'm actually not sure because we've not measured distances that far yet, but according to theory and maths, that should work, I suppose. But I think Anna and Eamon would both be better equipped to answer that than I am.
Yeah, I'd like to answer that. Let me tell you straight away that we have actually teleported a quantum particle, which is basically entanglement, from the Earth to an orbiting spaceship. 5 years ago, 5 years ago, two entangled particles, one on an orbiting spaceship and one in a laboratory in Tibet. The Chinese did it, and it's amazing. Now, you imagine how far away that is the farthest communication we've ever done, which is about 200,000 kilometers, I think it was. I might be wrong there, but it doesn't really matter because we're talking about quantum particles. Imagine how far away, 200,000 kilometers is to a quantum particle. So we're pretty confident, although obviously we haven't gone to another galaxy and tried it out, but it's almost certain that there's no limit to this. And I might add, there's probably, not only is it distance doesn't mean anything, probably nor does time. i.e., you can entangle two particles and have a time difference. There's a very, very interesting experiment that was only done 20 years ago, the delayed choice quantum eraser, which used entangled particles as you would in the double slit. But they used entangled particles, and they found that at a quantum level, events that have already happened can be altered. This is what we're talking about when we say reality is weird and we don't have all the answers. So thank you very much for that question, Ellie. Anybody else? Any other panelists?
I have a question.
Yeah, go on, Jane.
Okay, I was thinking about something with the so with the ability to have two particles be entangled with each other. I was thinking about the scalability of that, and if you could, because theoretically there getting bigger and more advanced, right? And so I heard that you could run a basic language on it, or they've got basic languages which are starting to interact with Python and stuff. So I was thinking about like converting from a digital signal to this kind of like different, almost not digital format. And like what possibilities could that have for like cloud streaming and stuff? Because you almost could like, I'm just thinking, would you be able to transmit data over not the internet? And it kind of like, it's like, would you even need internet infrastructure to be able to like stream content over like the entire world?
Wow, what a question. Anna, I think you're best to answer this.
Yeah, but I'm backstage. I don't think you.
No, you're not anymore.
Okay. Great question, Jane. The quantum internet is coming. It's going to be based on photons, the transmission of light, and it will change the nature of. It'll greatly increase by a factor of 1 trillion the amount of information that can be shared and spread around the globe. So quantum will make a big difference on the internet. There's a lot of engineering that has to be done before we get to that point, however.
I'm thinking how that could even like affect like rural communities, like somewhere in the middle of Australia or in the middle of Africa, you could have internet theoretically without having to have all the cell towers around you and all the infrastructure.
And I'm thinking on the moon. I'm curious to extend that a little bit further, Jane. Space station, the moon, the internet, and blowing away.
Yeah, no, definitely that is possible. There's great work being.
Is that potentially? Sorry, Anna. Is that potentially where we're going? Sorry, I'm just still with that. The quantum internet.
Yes, the quantum internet is coming. We're still going to need electromagnetic radiation, whether it's radio waves, microwaves, or light. As far as we know, that's the only way to transmit information, is to either send particles or send electromagnetic waves. So I think we're stuck with that. Elon Musk is launching satellites by the thousands. His goal is to bring internet to every location, every rural location in the world. Now, I'm not a supporter of Elon Musk as a person because of some of the things he's done, but his technology is out of this world.
Excellent. Any more questions? Yeah, Ho?
I had one on, so how do we know, like, if the particles are in multiple states at once? If when we measure it's a definite position, like, how do we get to understanding that if when we measure it, it's in a definite position?
Okay, Sadia, would you like to answer that, or?
I don't know if, okay, yeah, I'm there now. Could you repeat the question? I think there's a bit of lag on my end.
So it's just, how do we know that the particles are like, you know how the coin thing, like how it's spinning? How do we know it's in multiple states at once if when we measure it, it's in like a definite state?
So there is this theory called the Schrodingers Cat. I'm not sure if you guys have heard of it, but basically it's when there is a cat, I guess. This isn't a natural phenomenon, but there's a kind of like a cat in a box and you've got a charged particle next to it, and there's a 50% chance of it going off and 50% chance of it not going off, and you kind of close the box with the cat and particle in it, and then you come back and you don't really know if the cat is dead or alive because the chances of the particle going off were 50-50. So it's kind of like we say the the cat is both dead and alive at the same time, unless we open the box or we measure the state of the cat.
Yeah,
That
just to
makes a
add,
lot of sense. Yeah, no, thank you.
yeah, just to add to that, Hope, there's an experiment called the double slit. And what it basically does is it captures whether a particle of light, a photon, is a wave or a particle. So what happens is when it's not measured, when it's in its normal state, and remember you're made up of these quantum particles, but it's there's a pattern on the capture screen which is an interference pattern. So physically you can look at it and it's an interference pattern. Then when you measure it, it immediately becomes one pattern. Two lines, because it's a double slit. I won't go into the whole experiment now, but you can immediately see it change because you can look at the interference pattern, which changes from a wave to a particle pattern immediately. And it's even weirder because how does that photon know it's the second it's being observed? And you know, there's I could answer. That's a great question, which I could spend hours answering. But we definitely know when you measure it, it becomes a distinct particle. But before you measure it, it's in what we call a really strange state called superposition, which is wave-particle duality. So it's a wave and a particle, and we know that for sure. And we know it changes whenever it's measured, observed. It's called the observer effect. But that's a great question. Any other questions? There's none on the chat at the moment. We need. Oh, wait a minute. Any questions?
I had another one, if I can ask another one.
Yeah.
I was wondering about the application of quantum computing in artificial intelligence, like especially because you've got all the breakthroughs in AI and the availability of it happening right now with all the cloud solutions, and I'm wondering, like, you can start to see them generating multiple frames to make videos, but we're still very much in that uncanny valley. I'm wondering if this, because I heard it kind of explained as if digital computers or classical computers are like a candle, this is like a light bulb.
Yes.
And so I'm wondering if it'll be able to bridge the gap into the uncanny valley and create videos that kind of can really cross the uncanny valley.
If I may answer that question, and then I'll put on Anna. The biggest thing that's going to change in 2023 is a thing called AQ. So don't say AI anymore, because if you say AI, it shows you're not up to date. AQ is artificial intelligence plus quantum. And that is going to change the world in an unbelievable way. And yeah, I could elaborate on that, but it really would just go on for hours. But just be aware that AI is going to take an absolutely huge leap forward and change things like medicine, the finance industry, everything we do. Would you like to add to that, Anna or Sadia?
I'd like to say something about that.
Yeah.
I was deeply skeptical about the application of quantum computing, machine learning, and artificial intelligence. And the reason is because it's big data. You have a lot of bits, and quantum computers don't have very many bits yet. And so I was skeptical about it. But some of the leaders in the field have come out and said that it's a real prospect, a real possibility.
Yes.
And I have to look at it. Now, there are only a handful of quantum algorithms that are really well understood. And so, frankly, we just don't understand entanglement and superposition and their implications for well enough to know what will be the impact of quantum computing.
Okay, we're getting a lot of interference at the moment, Anna.
I think there's a plane going over or something.
Yeah. Roger, would you like to ask a question? Is there anything on your mind or just a comment?
Yes, I'm a bit confused.
Yeah, that's normal.
With with the how what exactly is it that the particles are doing when they're entangled? Like I don't know how to explain it. But
yeah.
Take your time.
I guess I'm just confused on the entangled with each other. How do we know that? Like I don't know how to explain myself.
Sadia?
Sorry, I don't understand your question. Do you mean how do they get entangled?
No, I don't understand like how we know that they're entangled, and like what are the instantaneous changes with each other, but what are those changes?
Right, so we kind of know when two particles are entangled with each other when it's hard to explain, but sometimes you know because you've kind of created a pair of entangled particles. Like I know people can create them by cooling them to a point where their wave functions, as I like the description of the particle, they overlap. So it kind of essentially becomes a joint kind of particle. But we know that they're entangled when one is measured, the other one is measured in an opposite direction, and they pass the information about one being measured in a certain way to the other one, so it kind of does the opposite thing, if that makes sense. It's hard to explain, I think.
Yeah, that's exactly the situation. We get a pair of entangled photons or electrons, it doesn't matter, any quantum particle actually, and we can entangle them in a laboratory and then send them through fiber optic miles and miles away, or whichever way we want, it doesn't matter. As long as we don't measure any of them, they'll still exist. But as soon as you measure one of them, the other one will show exactly the opposite spin, because they're measured, and this happens every single time, and we've done it thousands and thousands and thousands of times. It's like you and I being in a different suburb and tossing a coin, and whenever you get heads, I always get tails. And that's what it is. Anna, would you like to, anything you want to add?
Yeah, I want to mention that entanglement has been on the scene since the 1930s, when quantum mechanics first came out, because they solved the wave functions for the electrons, like in helium, for example, and they're entangled mathematically. So it kind of fell out of the mathematics, and even though the electrons in an atom of helium aren't far apart, they're still entangled. And it was an early consequence of quantum mechanics, but nobody wanted to accept it. And that's why Alain Aspect and the others had to do those Nobel-winning experiments, because nobody wanted to believe it. They could believe it in a limited case, like for the helium atom, but they couldn't believe it on a large scale where the particles are distances apart. But it really falls out of the mathematics. That's what
that's excellent. We've just had a question from the audience. Say Ganesh Manda. saying there's a single wave function for the whole universe, as Everett wanted to put it. I can comment on that, or do you want to comment, Anna or Sadia?
Well, I've heard it said that when the Big Bang happened 14 billion years ago, all the particles were entangled, and most of them still are.
Yeah, look, to answer that question, say, what we're talking about, when you mention Everett, the Everetian interpretation is the many worlds interpretation. Now, what we mentioned before with the double slit, and that when you observe a particle, it collapses, which is called the collapse of the wave function. That's called the Copenhagen interpretation. We know it happens. It's happened since we started experimenting, and it has never, ever, ever not happened. So whenever you measure to try and find out superposition, you simply can't, because it collapses into a distinct state. But Everett said in about 1965-ish, and he said, and he was ridiculed, he said the many worlds theorem, and that is that this, what happens is both people who, the observer and the quantum object, become entangled themselves. And in their world, the particle collapses, like the Copenhagen says. But what he's saying is that only happens in their world. And every time there's an entanglement between particles, a new world is created, if you like. I mean, it's a lot more complex than that, but I can't go into it now. There are many, we know quantum physics is weird, and but we don't know what's happening. And we have interpretations. And the Everetian interpretation is the many worlds theory, which is excellent. So thank you very much for your question from the chat groups.
I want to say something about that.
Yeah.
When the particles are entangled, you have multiple universes. That's pretty much consistent with quantum computing. When you perform a measurement, you're selecting one of those many worlds, and that becomes your reality. It's wonderful.
Yes, it is wonderful. You cannot help. If you're observing a quantum particle, you cannot help but become part of that universe, which is distinct from other universes. And again, I just want you to take away from this how weird this all is, and the fact that we are all, everything you see, touch, feel, is quantum. So when we talk about the real world, let's be straight here. The real world is the quantum world. We're not made of atoms. We're made of quantum particles that form atoms. You may as well say, so it's just weird. Donna, do you have anything to say? We're going to close in about 5 or 10 minutes. So
I just, yes, I do. I did have a question for Sadia, and I suppose for all the presenters today. If I was a person, a student, and I wanted to learn more about quantum, I know Kwekwa have their 10 by 10 minute videos, which are really great for an introduction. What resources, where would you recommend that a student or anyone look for resources? And secondly, knowing they don't go down a wormhole that's not the right wormhole, so ensure that we
go to IBM.
Oh, Anna, you beat me to it. I was going to say the same thing. Go to IBM.
Q Experience, Quantum Experience, Qiskit. They have wonderful tutorials that are accessible for beginners and move on to more advanced levels. And you can write quantum software and run it on a simulator or even on a real machine if you don't need too many qubits for free. IBM is the leader as far as software and as far as education. There are other computers which are more accurate than IBM's computers, but if you just want to learn, that's the place to start.
Yeah, I was going to say exactly the same thing. You can all use a quantum computer today. You just go into ibm.com/quantum or check for, like Anna said, the Q experience. And we are going to have, Anna's going to, on behalf of Q Girls, is going to start giving us some lessons on what's called Qiskit, which is a Python-based language that quantum computers use, basically. And it's a real drag and drop at the entry level, and you can do your own programs. You can actually entangle quantum particles yourself, and somewhere in the world, two particles will actually be entangling, and they'll be manipulated by microwave pulses in a computer in any country in the world. It's fantastic. Great question, Donna. Okay.
Yes, thank you for answering. My brain's ticking. I'm like, yes, I can't wait to possibly work within our girls programming network and have some something there developing in 2023. This is a nice way to end the year with this panel and learning experience. Lots to think about.
Look, absolutely. And Anna's is a wonderful teacher. She just, make sure that the whole class.
And I suppose I don't know how much more time we have left. Do I have time for one more question?
Of course you do. Yeah.
Okay, fantastic. Because I suppose I am thinking about the programming, and at a high school level, we are introducing students to a variable, an if else statement. Is there a big jump? Because I'm hearing Python is similar to Qiskit. Is there a big jump between the two languages? What would it be accessible to high school students?
Well, Qiskit uses Python. You write your Qiskit software in Python.
Okay.
There's another language, the quantum assembly language, which is quite simple and which is important. But Python you get a lot of mileage out of Python for Qiskit.
Yeah, excellent.
To hear that we're in the right space and learning Python, because that's where we're sort of working with a lot of students with Python. So it's good to hear that make that step from Python to, well, quantum world internet.
Yes, you can.
I think
yeah, that's the absolute ideal way to do it. Okay, look, we'll wrap it up here. I'd like to thank so much the panelists and presenters today. You've all been fantastic, and it really, there are huge opportunities, as Anisha has shown us, there are huge opportunities. Donna and I and Anna are dedicated to getting you all up to a stage where you can do what you want in the quantum world. As Jeff Bezos says, this technology is going to change everything. If you want to join Q Girls, at the moment, just Donna and I are going to talk about a proper enrollment process. But at the moment, if you just go to the Kwekwe YouTube channel, if you subscribe to that channel, you will get all the latest and greatest on what we're doing. And we're going to be doing a big one on post-quantum cryptography, I can tell you. And also, Donna very kindly mentioned my free of charge 10 minutes. So it's a series of 10 videos of 10 minutes each explaining almost all that matters in the quantum world. And I'll be answering questions on each of those episodes. So there's a lot happening. Please subscribe so that you're being kept up to date. Tune in, because Q Girls is going to go viral. No question about that. I'd like to thank you all again and wish you all well. Enjoy your day.
Thank you.
Bye, everyone.
Bye.
Good night.